Hey everybody, welcome back to another round of physics, and let's get going. We are going to have to take a brief pause in terms of new physical ideas and take a slight detour into developing some mathematical ideas instead. Now, part of this, we could have applied some of these ideas, say, in the past term, but we needed to let your calculus kind of develop before really using some of those techniques. And namely, what I'm thinking about here are techniques of integration that allow us to start extending our abilities from point charges into what I would refer to as distributed charges. So, and I should say, instead of doing charges, you could also do this for masses. And indeed, maybe we'll run an example problem where that's the case. So without further ado, I want to remind you of what we did last time. We were dealing with a source charge equivalent to 3 protons located on the x-axis. And in particular, we are interested to know what the net force was on that 3 proton charge due to the presence of 2 other point charges, a negative 2e and a positive 4e. Now, I'm not redoing the problem, but what I wanted to do is highlight the process that we did in order to solve that problem. Namely, the first thing that we did was we said that we needed to find the relative position vector between one of the charges in the surroundings and the system. And notice we say pointing from the source, or I've fallen into some different vernacular here. You could say pointing from the surrounding to the system. In other words, we're looking for this relative position vector. Once we had that relative position vector, we could find the magnitude of that relative position vector. And bearing in mind Coulomb's law, that allowed us to find the magnitude of the force between those 2 charges. Now, also knowing the vector form of the relative position vector and the magnitude of the relative position vector, we could calculate out the unit vector pointing in that direction. And of course, because vectors require 2 pieces of information, a magnitude and a direction, we have now calculated the magnitude of the Coulomb force. We have the direction of that Coulomb force. And so putting the 2 together allows us to find the vector form of that force. Okay, good. Then, after that, the only thing left to do is to rinse, wash, and repeat. In other words, we do this process for every charge in our surroundings. So calculating the force between that charge and the system, next charge and the system, etc., etc., etc. And all that's left for us to do after that is to sum the individual pairwise forces between the system and the surrounding charge, and we're done. Okay? Now, I should say that for 1 or 2 charges, like we've considered in lecture, like we've considered in some example problems, this isn't so bad. But what makes this particularly painful is if we start adding, number 1, more and more charges, right? The more charges that we have to do in this summation, the more arduous the technique becomes. And you could say also the second thing that makes this particularly painful is that the entire time we have to worry about the direction of each of the individual forces. They're not always in the same direction. So those 2 things make it particularly painful. Now, the other thing that I should point out is remember that Coulomb's law that we've written down, that we've discussed, is only for point charges, right? If we have this expression right? These Q's that we find in Coulomb's law are only for point charges. So the question then becomes, how do we take this expression for point charges and use it to get an expression for what I refer to as distributed charges? Some vocabulary for you before we get into that. So the first thing the vocabulary that I need to introduce, and sometimes, this is really a notation thing, but it is something that you run across often. Okay? And the vocabulary is what I would refer to as density. Now you might say already, Greg, I know what density is. It is mass divided by volume. But there are plenty of other types of, first of all, very interesting physical quantities which we might want the density of. For example, I don't know, something like cost density. How much does an object cost per unit volume? And then you start thinking about, where have you seen cost density? Dollars per gallon, for example. You are dealing with a density, but it's not mass, rather it's how much money. What I mean for this to kind of expand your brain in the sense of you've dealt with densities before, but generally it's been mass densities. I want you to start thinking about there are other interesting physical quantities that can be expressed in terms of density. Okay. Now, we'll return to the idea of mass density, but for example, here in Gen Phys 2, we're going to be particularly dealing with things like linear charge density, the amount of charge per unit length that you find on an object. Or, now this is for one-dimensional objects, perhaps you have a two-dimensional object, a surface. Well, in that case, we're talking about areal charge density. Of course, you say, wait, Greg, what happens if I have a volume? You can see the pattern. We're talking about a volume charge density. Now, as we start off, when we start dealing with these ideas of distributed charges, we will go ahead and I will assume that the charge densities are uniform. Now, take a minute, ask yourself, what does that mean in terms of lambda, sigma, rho, if the charge densities are uniform? Good. What I want is that I will assume that these are constant values. So if I have some charged object and I only take, say, half of it, half of its length, I get some amount of charge contained in just that portion. But if I double the amount of the object, the length of the object, then I'll have twice as much charge. Well, let's go ahead and think about how do we approach a distributed charge bearing in mind this process that we've laid out. Okay? So imagine for a second that you have some sort of charged rod. Okay? And generally speaking, how this will go is that you'll have either the total charge and the total length, okay? Or equivalently, you are given the charge density of the object. Of course, the two are related, as we've seen in the previous slide. The charge density, assumed to be uniform, assumed to be constant, is simply the total charge divided by the total length. Now, let's say, for example, we would like to find the total force of this charged rod on our system. How conceptually would we go about calculating that quantity? Well, first off, let us not consider the entire object. What we are going to do is conceptually, we're going to take that continuous object and break it into small chunks. Okay? Imagine taking that entire rod and cutting it up into tiny point charges. Okay? Now, the first thing is, after we do that conceptual division out, what we need to do is say, how much charge does this point charge have? Now, I've labeled it as a delta Q. Okay? But the question, how can we relate the amount of charge in this tiny little segment, which I will call dx? How can I relate the charge to Q total and L total? Well, we have an idea. Remember, because there is a constant of proportionality between the length that we've chosen and the amount of charge, we can calculate out everything that we need. Now, that constant of proportionality, again, is lambda. So you could think of, I'll start off with, maybe the easiest math equation. Lambda is equal to lambda. But over here, right, we have Q total divided by the total length. And over here, what we'll say is that I have a small chunk, delta Q, and I'm taking a small length of the rod. And so we see that the expression for the amount of charge in that little blue rectangle is simply lambda times the length of that rectangle. Pretty cool, huh? And that little transition will allow us to solve this entire problem. Now imagine for a second, yes, I will introduce the notation now, because you could say, well, this is if I happen to divide my beam rod up into a finite number of chunks. What happens if I decide to divide it even smaller sections? And I keep going, even smaller, smaller, and smaller. In fact, I will do it so that they're infinitesimally small. And what that means is that there is an infinitesimally small amount of charge related to an infinitesimally thin piece of the rod. And so, again, you know this. This is mathematicians. This is physicists being lazy. We want to distinguish between a finite size object and an infinitesimally small object. Okay? Good. So now we have an expression for the amount of charge in that little piece. Of course, we can get a direction. Assuming that both of these are positive, I'll explicitly put in the positive sign for a second. We also have to figure out how to get the direction of the force due to this point charge acting on that point charge. Now, conceptually, you say, well, I know that because they're both positive, that it should be pointing something like that direction. And also, you say, well, we need to get a relative position vector between this charge and that charge. Now, I'll erase this here. Sorry, I had some animations behind the scenes. So conceptually speaking, what we have to do is chunk it all up. And of course, we have to do a summation. But if I do an infinite number of chunks, then this becomes an integral. Now you notice, as I have here, both of these, referring to the relative position vector and the r hat, both of those change depending on which chunk of the bar we wish to consider. So what we will need to do is come up with a function that describes the position of each of the source charges. I'll say that again. We will have to come up with a function that describes the position of each of the source charges. Once we have that function that describes the position, then we can find the relative position vector. Once we have the relative position vector, then we can do everything that we need to do. Now you say, wait a minute, Greg, how am I going to get the function of the position? No. It's not as bad as it seems. For this case, because we have set the origin at the center of the bar, really the question boils down to how far away, what's the expression to describe how far away this first chunk is from the origin. In other words, what's the position vector? Now you might be tempted to say, well, this object, this one chunk is located at a distance at L/2 from the origin, which I agree with, but that's not a general case. That is just for that specific piece. What we want is a more general case, and bear in mind, we're going to sum from one location all the way through to the other. So a better expression would simply be that the position vector of the, I'll call it the source here, is simply, I'll call it x, 0, 0. And now you see that we have replaced a specific number, L/2, with a variable, x representing the position at any given point along the rod. And don't forget, or maybe I should ask, where do I start looking at? Where do I stop looking at? A different way to say it is, what are the limits of integration for the position of each of those source charges? And you say, okay, the limits, I start at negative L/2, and I will have to add them all up until I get to a position of positive L/2. Okay. So let's put this all together for you. Okay. So what I have is that the position vector for the source, in a very generic sense, remember I needed a function rather than a specific number. And so I have x, 0, 0. Okay. Good. And of course, for my system, I have something like, I don't know, what do we have? 1, 2, 3, 4, negative 4. So I had 0, negative 4, 0. Now, how do we go at this? Once I have the position vector for both the source and the system, you say, well, the relative position vector is simply the position vector of the system minus the position vector of the source. So I end up with something that says negative x, negative 4, 0. Good? And of course, now if I need a magnitude of that, well, that would just be x squared plus 16 square rooted. Okay. Well, let's keep going. Because of that very small charge, every small charge contributes a tiny amount to the net force acting on our system. So we have a very small infinitesimal force due to, and now I'll go ahead and write out Coulomb's law here, I'll call it dq, right? Because that is the small infinitesimal sliver of the bar that we've considered. I'll put in here system, and of course we have the relative position vector squared, and the relative position vector hat. Well, let me go ahead and plug in all the numbers. Okay. Numbers, variables. I'll leave k as the original. Now, we've already argued that dq is related to the width of the section that I've taken. And so I can replace that with something like lambda dx. To be continued. Very important. Well, q of the system remains constant. That's just some sort of point charge. And I have the relative position vector, magnitude, and the vector form. So what I will do here is I will go ahead and put x squared plus 16. And then you get a square root and then a squared. And then the unit vector, we remind ourselves, any vector can be turned into a unit vector by dividing by its magnitude. So we could think of this as simply being our vector, our relative position vector r, again divided by its magnitude. So at the end of the day, we get that the force due to that infinitesimal little sliver is equal to k lambda q of the system. And then I'll go ahead and plug in everything else. Okay? What we have is something like negative x comma negative 4 comma 0, all divided by x squared plus 16 squared. And we got a square and then another one. Okay, so that's to the third power. Right, 2 and then a 1 here. So we get, that's all raised to the third power, and then the square root is a 1/2. So to the 3/2 power. What is the last piece that we need to do? It is that is just for the small infinitesimal sliver at the end. What happens about the sliver next door, or the one next door? In other words, we need to now perform the summation. I have an expression, very generalized, that gives the force of a small sliver of the source charge acting on the system. Now I need to go through and add up all of the contributions from all of the source charges. In other words, we say that the net force is the summation of all these little individual forces. Okay. Very good. Okay, well, hey, I'll leave it there, but we'll continue on this little journey, and of course we'll have practice problems and all that kind of jazz, but yeah, to be continued. In any case, I thank you for your attention. Keep up the good work. I'll see you next time.